Okay.
Okay. So this brings us to the last part of this discussion. It's not going to be a long one. However, it's going to be, in my opinion, the most interesting one, as SP is directly involved in that. Petroleum engineers are involved in the storage part of this business. So to recapitulate, we have discussed about the need to do something with the CO2. Need to do something means simply that we firstly need to capture it. Secondly, to do something with that before storing, for example, EOR, beverages, or other utilization techniques, and eventually come up with the most difficult part, which is storage. Now, what does storage mean? Well, storage basically means that we are interested in utilizing subsurface reservoirs. The simplest examples of all is just case one. As you can see, if there is a depleted oil or gas reservoir, that means that its pressure is going to be now much less than what it used to be on day one when it was found and exploitation started. So a good idea is to, since we have taken out oil and gas, let's refill it with CO2. How much CO2 can be introduced there? Well, as much as we can inject, provided that we do not affect the integrity of the reservoir. Simply speaking, we don't fracture it, because if we cause fracturing, then there's going to be a leak. And of course, we're talking here about the idea of permanent storage of CO2, possibly for the next thousands of years to come. So we need to be very cautious when using systems like that. Second option is use CO2 for EOR, as explained before. Now, in that case, we need once again to think, how much CO2 can we store? Well, if we start injecting CO2, then it will push the oil and it will get mixed to the oil. But unavoidably, one day, this CO2 will arrive to the production well and it will be driven at surface. In other words, the CO2 that you will have stored permanently will have breaking through the system and will appear at surface once again. Well, it's not really like that, because the CO2 that will appear back at surface will be re-injected and so on, like this one. Now, this quantity can be considered as a permanent storage of CO2. That's why we're interested in solutions like this one. Third one is the most promising one, deep saline water aquifers. Simply speaking, we're talking about reservoirs, which, however, now contain saline water. We're talking, of course, about the deep aquifers, not the ones we just use in everyday life just to drill and get some fresh water, potable water at home. So in a case like that, the good news is that those aquifers are huge. They extend in an extremely big footage, which in turn means that the quantity that we are able to store in there, potentially, of course, is going to be huge as well. And this is why, basically, this is the first choice for all people that are involved in this business. Now, solutions 4 and 5, I'm not really an expert to discuss about. It has to do with coal seams, unminable ones, where for various reasons CO2 can be stored, but I wouldn't endanger talking more about that since I don't really know about that. Well, the sixth option is once again injecting CO2, but storing it in some, let's say, more strange structures, such as shales or some cavities or even basals. In other words, we're not talking about the typical structure of a reservoir. Okay, so those are the options. I guess that quite many people out of you have heard about this crazy constraint that if CO2 is to be stored in a subsurface system, the depth needs to be more than 800 meters. The question is why? How did this constraint appear in the discussion? The idea is very simple. The reservoirs are hot, and the deeper we go, exactly due to the geothermal gradient, the temperature becomes even more than that. So if you're about to deliver CO2 at that depth, it needs to be dense. But dense at high temperature cannot be achieved in the liquid phase because the operating temperature is very high. So you're going to be living in the supercritical region. So the question is the following. If we have an understanding of, say, the average density of CO2 at supercritical conditions, what's going to be the depth we need in order to go above the critical pressure? This is exactly what is shown here. The pressure of the CO2 is going to be the gradient of that times the depth, and it needs to be more than the critical. So if we solve this equation, simply we're going to see that the depth needs to be approximately more than 800 meters. Of course, for safety purposes, one does not rely on this number, but we go even deeper just to be sure about that. Now, let me insist a little bit on the density issue. We all know that gases are compressible, are highly compressible, which means that if we increase the pressure, their volume goes drastically down. At the same time, we do know that if we increase the temperature, their volume goes up as well. So we have a contradicting effect between pressure and temperature. That means that as we go down into the subsurface, and if we assume a geothermal gradient, the typical one, of 25 C per kilometers, starting from 15 C, and we also assume the hydrostatic pressure, 0.45 psi per foot, then in that case, this is the relative density of the CO2. So if we take a volume which is equal to 100, whatever volume units might be, at a depth of 2.5 kilometers, it will occupy only 2.7. In other words, this corresponds to a factor, I don't know, probably close to 35 or so. So your density has increased by 35 times. This in turn means that in the same volume, the mass that will be contained now will be 35 times more than what it used to be at surface conditions. So that's the good news about the subsurface. We get optimal conditions, or at least favorable conditions, which allow us to get high density. So in a limited volume, we can store more mass. It's also interesting to see in this chart that below 800 meters, we get more or less a stable behavior of the density. This is exactly the transition from the gas and the liquid phase to the supercritical one. So that's the reason why we need to rely at depths below this one. Okay, so now we get some understanding about the variation of density with depth. Let's use it to run some simple calculations. So suppose, let me direct you with this chart. Here is a typical well that we might use in order to inject the CO2. So CO2 needs to be injected by the means of compressors. It's going to be at the beginning in a gas form. So we need to increase its pressure accordingly so that the pressure with which the CO2 will arrive bottom hole will be enough for the CO2 to flow inside the reservoir and get trapped there. So at the end of the day, we need pressure to be applied at the top. And the question is, how much should that pressure be? Well, through an Excel calculation, but what I will try to demonstrate is that by using very simple principles of just physics, high school physics, I would say, we can come up with some estimations of those values. Let me show you how. Now, this is the axis of depth. We start from the ground, going down to 3,000 meters. And here is the pressure that accordingly increases according to the typical gradient. Now, in the horizontal axis, we got the temperature. And the temperature is, in this case, is in F, Fahrenheit. So the temperature at the surface is the typical value of 60 F. So let me start with the blue line. The blue line depicts how temperature changes as we go down. It is just only due to the thermal gradient. So that means that at the injection point, if it's going to be at, say, 3,000 feet, the temperature will be that high, 180, maybe more, slightly more than that, degrees F. So your fluid will arrive at that pressure and at that temperature. And the question is, in order to do that, what should be the pressure at the top? In order to arrive here at the pressure of, how much is that? Close to 4.5 thousand psi, which is the pressure prevailing at the required depth of 3 kilometers, and at the temperature of 180 F, what should be the pressure at the top? Well, clearly, the pressure here is the pressure at the bottom minus the hydrostatic column here. The hydrostatic column can be easily shown by the red line here, the slope of which has to do with the density, the average density of CO2 at that depth. So simply speaking, in order to force your CO2 quantity to arrive at 3,000 meters, where the pressure is 4.5 thousand psi, you need to inject it at surface, supposing that it is cool, at the pressure of approximately 1.4 thousand psi. So you need compressors. Okay, that's the moral of the story. You need compressors, and they're going to cost you extra money. And to make things even worse, it's not really one compressor. You need to set up many compression stages, and you need chillers as well. And this will increase further the cost. So it looks like we have a big amount of extra cost just at the top of the injection well. One could argue, just a moment, we're talking about the compressors to inject the CO2, but is there a well? My answer is no, there is no well. We need to invest on the well as well. So we need more money to drill the wells. So it's not an easy game at the end of the day. That's why people are struggling to find even more profitable solutions, or better say, less costly ones. Will make things even worse. Apologize for that in advance, but we need to be more realistic. The question is, if those are the prevailing conditions at the bottom hole at this point, should we inject CO2 at exactly that pressure? Well, not really. Just think that by the time we inject the fluid here, it needs to exhibit a pressure higher than the static one so that it can flow. So it has to do with the so-called injectivity of the well. Now, if the permeability here is good, this will cost you only just a few hundreds of psi. But if the permeability here is low, just remember the case of the shales that I discussed about before. That means that you're going to need a lot of additional pressure here. To get additional pressure here, you need to have taken care of that at the top. Simply speaking, instead of using the line of pressure that was devised before, we need to shift it lower so that we are going to establish an extra drawdown in order to make sure that CO2 will be able to flow in the reservoir. So can you see how things are getting worse and worse? I mean, we started with a pressure of 4.5 thousand, and we ended up with another, say, 1,000 psi more. So you need more compressors, more energy, more capex. It can be even worse. Take a look at those pictures, and for those of you who have been involved in production engineering, they should look quite familiar because it's just what happens in the interior of a well, and this is what happens at the wellhead. So simply speaking, if you're about to use your well in order to inject CO2, you need to invest more money for some special piece of equipment. There are several things that we need to consider if we are talking about injection rather than production, as we regularly do as petroleum engineers. For example, take a look here. Those are the packers which isolate the annulus of the well from the bottom hole of that. Now, we need double grip packers, and the reason is very simple. If you inject CO2 here, the pressure will be very high. So you're going to have a high pressure here, a low pressure behind the packers, so the packers will be unset. And you need to reinforce the grabbing of that. Similar arguments hold for the wellhead. You need extra pieces of equipment. in order to compensate the switching from production wells to injection wells. Nevertheless, suppose that we are successful at injecting the CO2. What happens next? What will happen to the CO2 that will be injected? We need to figure out what are going to be the drive mechanisms. I mean, okay, the CO2 will be stored there, but by what mechanism? Let me give you a brief understanding of that, and then get into some more detail in each mechanism separately. So, by the time that you inject CO2, CO2 cannot move right away because you're talking about flow in a porous medium with some limited permeability. So initially, it will be concentrated around the injection well. Therefore, it will generate the so-called CO2 plume, like this one. Now, as time goes by, there's going to be movement of this plume. Why is that? Well, it's simple. If the CO2 is here, it is lighter than the water that already exists, or even the oil that already exists in the reservoir. So it will try, if we're talking about a depleted one, of course, and CO2 will try moving upwards, exactly due to the buoyancy. Simply speaking, it's gravity. So it will be driven at the highest possible elevation inside the reservoir, and in a quite long period of time, it will arrive into the green position shown here. Now, this is what we call structural trapping. In other words, it doesn't move simply because it is trapped physically by some kind of sails or by some kind of faults, probably. However, this comes the interesting part now. Since the CO2 is going to be moving here, that means that water will invade back this area until new CO2 arrives. So, simply speaking, this area will be rinsed with CO2 and water alternatively. For those of you involved in reservoir engineering, probably you are familiar with the hysteresis loop, drainage and inhibition. Simply speaking, when the CO2 goes through the porous medium, there will be some specific permeability. When water follows after that, the permeability will have changed, or better say, the flow properties of the fluid. Exactly due to that difference, it is some quantity of CO2 that will be trapped permanently in the pores. And this is what we call the residual CO2. So this is an entirely different mechanism that applies, but it does account for some considerable amount of CO2. So people do consider that. A third option is the following, which is, I would say, even more interesting. Suppose that the CO2 has climbed here at this position and is trapped structurally or stratigraphically. Now, what's going to happen? Is it going to stay there forever? No. There might be hydraulic equilibrium, but there is no thermodynamic equilibrium. That means simply that CO2 will get dissolved into the water, if we're talking about the saline aquifer. So if CO2 now gets dissolved in the top layer of the water, that means that that film, that layer, will become heavier. If it is heavier, it will go down. And if it's going down, that means that there are going to be fresh saline water, which will climb up to take the position of the previous one. So we're going to have a recycling of water in there. Water from the bottom will be driven up, and water at the top will be driven bottom. And each time, fresh water will climb up, and it will dissolve even more oil. So we would call it an automatic mechanism based on dissolution, of course, which is another good reason to store CO2 in saline aquifers. Basically, those are the three major mechanisms that are used to ensure storage of CO2. There is one more, mineralization, that we're going to discuss about in a minute. So if we get a vague, fair understanding of those mechanisms, let me show them in some more detail. Structural trapping. We simply inject the CO2 and the CO2 is simply stopped, doesn't flow anymore, exactly due to the presence of a sealing caprock, shales and evaporites or whatever. Okay. Now, what are the forces that apply in this effect? It's only viscous forces and gravity. Viscous forces are due to the fact that we inject the CO2, so we apply pressure. We cause those viscous forces due to the flow of the CO2. Gravity is there due to buoyancy. It is the reason why CO2 stays at the top, where saline water remains below. Now, for the residual trapping, as I said before, it all starts with the hysteresis, the difference between drainage and inhibition. At the end of the day, there will be some amount of CO2 which will have an entirely different interfacial tension compared to the original CO2 plume, and therefore it will be trapped here, regardless of the viscous forces. You might be applying pressure, it won't move. Its relative permeability, simply speaking, will become equal to 0. So it will be trapped. And believe me, we do like this trapping mechanism more than the previous one. Why? It doesn't move under whatever conditions because it's trapped by capillarity. On the other hand, let me go back to the previous slide. If something goes wrong here, if there is a crack, if there is a fracture in the caprock, the CO2 will leak. So this is prone to leakage. This one is not. That's why we do like that. So we need to consider the relative strength of each one of those mechanisms. Let me get back now to the dissolution trapping. CO2 is dissolved into water. And as I said before, the brine that is saturated with CO2 is heavier, goes down, and fresh brine will go up. So we are going to have what we call a convection effect, because we got, not from the thermal point of view, it's not heat that is transferred, but it is CO2 that is transferred by this cyclic motion, which takes a very long time as well. What are forces now? Thermodynamic equilibrium and gravity, and this is what causes this convection effect. The last mechanism is something which sounds very nice, very promising, but it has a major disadvantage. So it's called the mineralization. I guess you have already understood from the word itself that the idea is to convert CO2 to some kind of mineral. So what we are talking about is chemistry of minerals. Well, please accept my apologies for not being able to provide more information. I'm not an expert in that. So chemistry of minerals is one of those terms that made me feel very uncomfortable. So I won't dare talking about that. Just keep in mind that there are two schools of thinking, let's say, two different directions towards mineralization, the in situ and the ex situ one. In situ simply means that we expect mineralization to take place inside the subsurface reservoir. Ex situ is the following. If mineralization is about to work by itself in a reservoir, why not use that on our own? Why not attack it at surface by our own devices? So this is what people are trying to do, store CO2 by mineralization, but do that at surface conditions. Okay, so I guess you get an understanding of the four basic mechanisms, trapping mechanisms of CO2. Is it as good as it sounds? Well, not really. There is always the great danger of the CO2 migrate through faults. For example, this might be a good saline aquifer, which, however, has a fault through which the CO2 might be able to travel upwards. So in that case, what would happen eventually? If through the fault the CO2 goes up, hopefully it will be trapped structurally by another impermeable layer that might lie above that. So it looks like we started with a single plume, but we came up with two plumes. Now, I guess some of the CO2 will escape even from this second trap and it will concentrate it in a third trap or even in a fourth one. So at the end of the day, exactly due to the migration through faults, what we come up with is not just a single reservoir or a single plume, but we get many plumes which are interconnecting, usually through faults. Is it good news or is it bad news? Well, at the first glance, one might say it is just bad news simply due to the fact that CO2 goes up. And if it goes up, I guess that one day it might arrive back at surface. So that's going to be a catastrophe. Well, from another point of view, we should also take into account the fact that if the CO2 migrates upwards like this one, then we get more space for CO2 to be stored. So what's the moral of the story? Since we don't have information about those sealing layers, we need to get very often through geophysics studies. And people use seismics, and they also use gravimetric methods in order to come up with some understanding of the position of the plume. They do that all the time. It costs money, but it's the only way to get some understanding of what, at the end of the day, is the location of my CO2. Okay. Please also keep in mind the following. Unlike a typical oil reservoir, which has been exploited for 40, for 60 years, where there have been dozens of drilled wells, dozens of geophysical surveys, where we have plenty of information about the whole structure, this is not the case with the saline aquifer. The information we get is very, very little. And this is why you get a great danger that we miss the fact that there is no really real sealing effect. Just to give you an example, where is that? Here? Oh, pardon me. Sleipner, Norway. Sleipner is here, is a huge, really huge reservoir, saline aquifer reservoir, which has been spotted by Norway back in the 90s. So they get the advantage that they have been developing the whole area with crude oil and natural gas production. So they have been going through geophysical surveys. There have been a lot of information. That's why they dared do something like that back in 1996. They injected the plume at a depth of below 800 meters, as explained earlier, down to 1,100 meters below the seafloor. Okay, the plume was found to ascend by 200 meters ever since. Believe it or not, it climbed up by 200 meters. It breached various shale barriers, the thin ones, which had a thickness of the order of 1 meter. They look like as they never existed. They just breached like that. So today, as we speak, there are 9 distinct vertically stacked CO2 layers. Increased storativity, but the danger that one day it might arrive at surface. And this is going to be a great disaster, okay? So, no, let's keep it, it's quite technical. Let's go back with this one. Let's introduce time in this discussion. It looks like we get 4 different mechanisms. Which prevails? Well, it's a question of time. At the beginning, what we got is just structural. So there's a plume that moves inside the porous medium. But as time goes by, as CO2 comes back and forth, exactly due to the hysteresis effects, we get residual trapping that goes up. So at the beginning, the most part of the most dominant mechanism is just structural. As time goes by, we get more and more of the residual. Solubility takes even longer to activate. Due to the convection effect, it takes a long time for CO2 to roll up and down so that more and more CO2 can be captured. And it costs you in time. And we're talking about time, we're talking about not just decades, but hundreds of years. The most stable, the most secure, the most safe scenario is, of course, mineral trapping. However, as you can see, it takes really centuries or even millenniums in order to come in place. So we need to consider all that as time goes by, we have an increasing security in the storage. due to the replacement of the unsecured mechanisms with more secure ones, but we need a lot of time. Probably by that time we will have moved to some other planet, I guess, probably outside the solar system. I don't know, just good guessing. So are people really considering all those facts? Well, I can assure you that they do. For example, there have been studies where they divide the story, the expected future of the aquifer into stages. Stage one is when the early days of the life of the reservoir, CO2 is just injected. In stage two, some of that will have already been trapped. Later on, they also consider even leakage. And at the end of the day, they also consider chemical trapping by solubility or by mineralization. Once again, the question would be the same. How safe can those calculations be? They cannot, is my answer. It's like the case with oil. You just wait over time to get more data to understand if the path that you have projected in future time is correct or not. So it's exactly the same story as oil and gas engineering. Get data, interpret them, and infer what's going on down there. A last example that will help you understanding, especially the reservoir engineers of yours. This is the simplest application of the material balance method in order to just very, very simply estimate how much CO2 can be stored in a depleted reservoir. So suppose that the oil-water contact is here. That means that we get the aquifer, and above that, we got the reservoir. The reservoir has oil and water. So water is divided in the interstitial water, connate water, whatever you call it, and extra water that might be introduced during the last 30 or 40 years during a water flooding era. And this is the residual oil which is not able to be captured. So this is the point where the management says, okay, stop producing. It's not economic anymore. We have been through the payback time. That's good news, but the IRR is really bad, which means that we need now to do something else with this reservoir. Let's introduce some CO2. How much gas can we store there? Let us think. What's going to happen if we inject CO2 on top of this formation? Well, if the volume of a reservoir is constant as is, and to inject new stuff on top of that, pressure will go up, which in turn means that the existing fluids, like the remaining oil, the flooded water, or the connate water, will be squeezed. And it's a question of their compressibility, what's going to be the volume that they will occupy under the increased pressure conditions. So the interstitial water will be shrinked by a factor that depends on BW, the formation factor of water. The flooded water, the water due to the water flooding will be compressed by BW. Those are values which need to be known from the PVTs of the study of the reservoir. The remaining oil will shrink by BO. And the gas that will be introduced in the reservoir will be shrinked by BG of the CO2. Those values can be obtained from tables, from the experience, from samples. So, simply speaking, we can get all those factors. What about solubility of CO2 to water and oil? It is controlled by the Henry constants, Ko, Kw. So get an estimation of those, and there you go. The problem to be solved, therefore, is in order to arrive at the maximum P, what's going to be the amount which, when introduced, will squeeze all existing fluids, and at the end of the day, the volume will be retained. That's the material balance application. Believe it or not, all this description can be fit into a simple equation, which can be solved for the mass of the CO2 to be injected. Is it accurate? Well, not really. The same way the material balance method is not for an oil reservoir, but it gives you an excellent, very brief understanding of how much is, more or less, just give me an order of magnitude of the amount of CO2 that can be stored in a depleted oil reservoir. There has been an entirely different option which has been proposed. As far as I know, it hasn't been applied yet. It is at the lab scale, which is really interesting. However, it's a very, very promising one. The idea is the following. If you're familiar with hydrates in a big scale look just like ice. Those two here look just like ice cubes. But what gets inside here is that we got water molecules which are combined to generate those cells. And each cell occupies at the center a single CO2 atom. So in other words, we have, due to hydrogen bonding, we have water molecules that generate a cage, and it encapsulates in the middle just one molecule of CO2. So how is this formed? Well, naturally, it's a physical operation. The only thing you need is low temperature and high pressure. So simply speaking, if you provide me with CO2 and a water stream, plenty of water, and you provide me also with the time, low temperature and high pressure, I'm going to generate hydrates for you. If the hydrates remain stable in infinite time, that means that you have just accomplished your CO2 storage task. Your CO2 will be permanently stored exactly inside those cases. So that's really a very good idea. Good. Is it that simple as it sounds? Not really. Just to give you an example. Take a look, please, at this chart. This is the depth.
Mr. Gaganis, sorry to interrupt you, but we have 10 more minutes.
Oh, okay. I'm going to skip that then. And
I'm
just,
sorry. Yes.
Yeah. Well, okay, nevertheless. So, hydrates can be formed, for example, in the deep ocean. At this point, how is going to be done? Simply because at this point, if you run a few simple calculations, you'll find that the conditions are favorable for hydrate forming. The question is it going to be stable or not? For example, if for some reason there is some heat coming out from a volcano, it's going to distort the equilibrium, so the CO2 might be liberated. Do we like that or not? I don't know. Probably you remember the case with the Neos Lake back in Cameroon back in 1986, where CO2 was trapped at the seafloor, at the lake floor, and due to some earthquake, it was dissolved. It didn't. Oh, pardon me. It went up, and then it killed everybody at some distance of more than 10 kilometers, if I can recall well, 15 kilometers. Nothing from people and livestock were left alone. So the moral of the story, we need to be very cautious with those ideas because stability has not been guaranteed yet. This brings us to the conclusions. Now, there have been many actions from many associations like IEA, like the European Union. Already quite many countries have been investing money into CCS. It's getting some momentum, the CCS business, but slowly. We already discussed about Sleipner and what happens with that. And Northern Lights is currently a milestone project for Norway because they are aiming at storing 5 million of tons of CO2 per year. Of course, we're talking about saline aquifers. What's the conclusion? Well, is a miracle machine or a white elephant? The answer is, I don't know, but we do know that's a necessary tool to meet the net zero target by 2050. If this task sounds too ambitious, then at least we need to work hard on that in order to somehow mitigate the global warming effect. And something which is probably the most important, I guess it's the most important slide out of all those that I have tortured you with today. Take a look at the engineering disciplines that are involved in CCS. Drilling engineering is there, we need new wells. Production engineering to make the CO2 travel down, be injected. Geology to find the targets where we need to inject the CO2. Petrophysics to get some understanding of permeability and porosity. Porosity is directly related to the quantity of CO2. Reservoir engineering to be able to monitor what's the location and the evolution of the plume. Fluid properties like densities, like viscosities. geophysics to understand the location of faults. Simply speaking, all petroleum engineers can directly switch to CCS. It's going to be quite easy for anybody involved in the business. Myself is one of those who are gradually switching, well, not really switching, but getting involved in CCUS. So I can advise you to do so as well. So the moral of the story of the talk, CCUS is here. It's live, it's kicking, and it will be here for the years to come. Be prepared, get information about that, get ready, and get the pole position if possible. With this, I'm arriving to the end of this presentation. I hope that you have enjoyed at least some part of that. Thank you very much for your attention, if I really got it, and I will be glad to hold any discussion and answer to those to any questions if possible, of course, and certainly if you have some.
Dr. Gaganis, unfortunately, we don't have time for questions because at 8 o'clock the meeting will stop.
Actually, Mr. Yotis has a question. If we can, I don't know.
Thank you, Vassili. Thank you very much for this very interesting and all-inclusive, holistic approach to the problem. Unfortunately, it is a bit late. I would propose we still have a few minutes. Maybe we can have 1 or 2 questions. I don't know.
I would be happy to.
I can see also that we have, the dean of our school here, Professor Galetakis. We have Professor Pasadakis. So I want to thank them as well for their participation, and all the audience as well. But maybe we can take 1 or 2 questions. Yanni, you have the questions, maybe?
I think Mr. Jose Tarola wants to ask something. I saw a question in the chat. Would you like to express it directly to Dr. Gaganis?
Just let me take a look to that.
I would like to. Okay, as far as I could follow on the presentation, especially what it's related to the capture stage of the process. If I understood correctly, most of the efforts have been focused in the moment where you have the energy production. However, the moment, this might be a little bit out of topic, but taking in consideration that until we reach this point, the production chain that leads to this point, I mean, when we obtain the coal, when we produce the oil, when we create the facilities for the energy production, each one of these steps has already a big production of CO2. Most of the patents that were mentioned are focused also on this point. Are there any efforts focused on capturing and leading to the storage of CO2 focused on all the previous stages?
Jose.
Yes.
Long time no see. It's really a pleasure to meet you even through this system. It's really a pleasure for me. So thank you for your question. Basically, you're absolutely right that there are dozens of emitters. However, people still, the research also focuses on all possible emissions of CO2. In fact, what they're interested in is setting up methods which do not really depend on the source of CO2. However, there are some technical obstacles which render the power plants as the perfect candidates to work with. By the way, let me clarify something. When talking about power plants, I'm not really talking about generation of electricity for the public, for example. Just to give you an example, in a refinery, there are units which produce heat, okay, not for energy purpose, just for heating the oil or for using the distillation columns and stuff like that, okay? So those are good points to capture the CO2 as well. I just used it, I need to apologize for that. The term power plant, I gave the impression that I'm talking only about generation of electricity, okay? Any kind of generation of heat is a good candidate. There is, however, a big issue that all methods depend on. It has to do with the concentration of CO2 in the flue gas stream. I mean, if it's of the order of 10, 12, or 15%, this is a quite good number, which means that there is enough CO2 to be captured from the flue gas, which in turn means that most methods are working fine. But there are many more cases, such as I just recently learned about that, the gas turbines that people use in the refineries, where the stream produced has only 4% of CO2. And most of the capture mechanisms, well, I wouldn't say they fail, but they not perform as well as they should. So basically, this is the reason why we prefer the power plants. We got good. Come on, let's rich CO2 rich stream.
To make the effort, make it worth it. To make it worth.
Absolutely.
Okay.
At the end of the day, it's a cost-benefit analysis issue, as always. Okay.
Thank you.
Hope this answers your question.
Yes, yes.
Dr. Gaganis, we want to thank you very, very much for this very interesting presentation today. It was a pleasure having you with us today. Unfortunately, we have many questions, and we don't have the time to answer them. Once again, we want to thank you.
Maybe we can send them to you. I don't know if you and we can upload
If it's worth
the
doing
answer.
so, we'll be happy to. Okay, just feel free, Andreas.
Thank you so much. If there is
Thank you.
so much, so many questions from the audience, we have to do our best to answer them.
I see. So it's my pleasure to be here. It's my honor. As I said before, I truly mean that. Well, you know that I've been part of this university for quite many years, and still a part of my heart is still there. So getting the chance to be into contact with that is more than just being happy. Okay, so thank you very much once again for your presence and your attention. Okay, thank you.
Thank you. Good
Thank
night
you.
to everyone.
Bye. Good night.